say, okay, sir. So basically, we looked at here. Let us try we are replacing something here, but we will have full this kind of systems. You will say, sir, okay, we need this kind of architecture here. See, so this architecture you now mimic this CC bond and CH bond. So 3 sigma architecture here. Then what do we say? We need one p orbitals here, vacant p orbitals. If this is vacant p orbitals, then it will bypass the electron delocalizations. So 1 plus 1 vacant p orbitals. Vacant p orbitals. This is your demand. Then what will you do? Now you know a lot of chemistry, you know. So which atom you choose? Let's say you have choose your nitrogen, because you know that nitrogen can have 3 sigma bond and 3 sigma orbitals on p orbitals. This is the nitrogen hybrid orbitals. So this is, let's say, its bonds formed from sp2 orbitals, this from sp2 orbitals, and this is also on sp2 orbitals. Then what we will have? As this is sp2 hybridizations, then we will have a pi bond. Basically, this is the pi orbitals. Now, here we have two lone pair here, as we need vacant p orbitals. Now you move it to your own way, own directions. Basically, now you think. So now you adjust these things here. If you put this nitrogen here, then what will happen? This nitrogen here. Now it has a p orbitals. That p orbitals will take part with delocalizations. It's okay. It have two same bond connectivity like benzene, and instead of benzene, where we have two lone pair in sp2. That's the real secret behind point atom mutation. So here, what basically we are doing, we are replacing one CH moiety by N. Basically, we are replacing one CH moiety by N, not N. Really, sp2 hybridized nitrogen, again sp2 hybridized nitrogen where the lone pair lie on sp2 orbitals. That's the complete definitions. Where the lone pair of electrons lie or resides in sp2 orbitals. Because your p orbitals, vacant p orbitals, means your p orbitals has to be vacant. Otherwise, it cannot take part delocalizations with these 6 ring electrons. That's the beauty of this replacing or replacement of hydrogen. Normally, if we see pyridine, if we say, so nothing comparable, we can see changes with benzene, but this is the difference. There is a totally logical replacement. So in the language of biology, you can say basically it's a mutations, it's a point atom mutation. Basically what you are doing, you are mutating, like biological concept, you are mutating, or CH moiety is mutated by N atom. Basically telling N atom is a wrong term, because N atom where this N is sp2 hybridized, not only that, where the lone pair lie on this sp2 hybrid orbital. This is the complete scenario. Now you understand, just after the immediate first class, why I described that this chemistry is as much as beautiful like that picture. And slowly you enjoy all the chemistry here in that way, as if someone is telling you a story and you are enjoying that things. Basically, here the chemistry is very much simple as well as interesting. Now you are brilliant enough, you learn that CH moiety can be replaced by nitrogen. You logically explain that, you logically understood that. So if you replace another CH moiety, by nitrogen, you can replace, then what will happen? Nitrogen here was already replaced, now one more nitrogen here. So this is different heterocyclic compound. Its name is, we should not be bothered about the name, but yet I am writing pyridazine. Okay, now understands it. Okay, then ask. So you have replaced this, and you are telling is it as aromatic as that of benzene. So what is the minor change? So in the previous classes, one of of your not previous classes, in somewhere in your BSc you have read about spectroscopy. Here by spectroscopy we try to understand what change happen here. Basically, look, we have a hydrogen, means three types of hydrogen. This hydrogen is at ortho with respect to this nitrogens. I shouldn't say ortho. These are 2 position, 3 position, 4 position. So this hydrogen is closest to the nitrogen. That's why as nitrogen is electron withdrawing or electronegative atom, I shouldn't say electron withdrawing, electronegative atom, then its electron deficiency means it will be electron deficient. It will have electron deficient environment. So this hydrogen has electron deficient environment. Deficient environment. So for this, delta H will be at higher ppm values. So the value is 8.5 ppm. And for this, look at the value. Here, the delta is 7.1. And here delta is equal to 7.5. You will say, why sir you are writing the 7.1, 7.5? I can understand 8.5 is okay. It's closer to nitrogen, nitrogen electronegatives. So this nitrogen has electron deficient environment. Then with respect to this hydrogen, this hydrogen is closer to nitrogen. With respect to this one, this is 1, 2, 3, 4 carbon array. Then we could expect the value should be reversed. But why it is like that? The reason is that basically this nitrogen, if this kind of delocalization happens, see what is going to be. This is N minus here, because this type of electron delocalizations, this carbon has quite positive charge. That's why this proton is quite electron deficient. That's why its delta is quite positive. And here, when you are delocalizing, you see this is always this carbon within to some extent with electron rich environment. That's why delta is value for this hydrogen is equal to 7.1. That is the lowest. That also one fantastic thing we can discuss. Okay, so we are happy with that. And now someone is asking, so sir, you told about the mutation of or replacement of one CH group. Then if I want to replace this group by something, then what is going to there, what we are leaving there? See, this system is here. These systems, because we are cutting this system out, this system. So if we replace some atom here, then we will have these things. Then with logic, how we can do that? Again, so here we are cutting with 2 electrons. Then we have to provide 2 more electrons. That is a pi electrons. So 2 more pi electrons, or not pi electrons, 2 more electrons in p orbital is required. If we have a p orbitals here, means let's say we have p orbitals here, and that has 2 electrons. It means it's equivalent, as if these 2 electrons is equivalent of these pi bonds. That's why we need 2 more electrons in what? pure p orbitals. Then again, your nitrogen is a good friend. What will do for nitrogen? If let's say we have a nitrogen, it will be sp2 hybridize, and this is the pure p orbitals. Here we have two electrons. So basically, see, here we will have NH, and this will be for CC bond formation, for NC bond formation. See, you take this skeleton, put it here. So basically, what we are doing, we are getting a p role, NH. That's the concept. So if I summarize, what we can do, what we can do that if we replace, let's come here. So if we replace one CH, one CH by nitrogen, which type of nitrogen? Nitrogen with sp2 orbitals with two lone pair electron in sp2 and vacant p orbitals. Then we'll get these things. So if we want to replace one CH bonds, we have to use these things. So it is pyridine. And if we want to replace these things, we are going to do the job again by nitrogen, where this is a fantastic guy. Here we need two electrons here. That's the fundamental difference. So this will used for the formation of NC bond. NC bond, this will be NH bond. Then we will have these things, a pyrrole, two lone pair. Okay. So that's because of lack of time. Just for the basic things, I have to stop it here. Just to believe me, the replacement logic is that much beautiful. Okay. Now, because so wait a bit, just I'm waiting because I have to attend one call. Maybe I will come back within 2 or 3 minutes. But please wait. Okay, thank you for waiting. So I hope you are in line also. Let's check it. I will keep. Yeah. Okay. Then basically it's a nitrogen. So you will ask now, you are very clever one. Normally these things we tell as imine. Imine. So imine is very unreactive, reactive. It's a reactive. Then you can ask, sir, so this is basically imine. So then it imine, but the molecule is aromatic because of this fantastic replacement strategy, or the molecule is aromatic. So this is basically now I am write down one fantastic statement. Pyridine is an unreactive imine. It's a statement they have quoted from the book of Claydon. So if you find some time, read this book. It is more interestingly elaborated there. Just because of our shorter time, we have to discuss that much. Okay.